Okay, so guys, a little while back at the beginning of the school year, we talked about functions and their derivatives. What's the derivative of this function? Okay, now that's a shortcut, and shortcuts are nice, and you're going to really appreciate the shortcut by the end of today, because the thing I'm going to show you is a lot of writing, okay? But the shortcuts are just that. They're shortcuts, okay? They're not really where derivatives come from. So what I'm going to show you guys today is how did mathematicians come up with this derivative, okay? And we call it the limit definition of a derivative because that's what derivatives really are. Derivatives are the result of taking a function, finding the slope between 2 points, and then finding the limit of that as those points approach the same point. And you get an instantaneous rate of change. So instead of getting an average slope, you get it to be an instantaneous rate of change. And so that's what we're going to do today. We've done it before already. We just did it graphically to get the idea in your head. I'm going to start that lesson the same way today, just to remind you. But then I'm going to show you algebraically how that works. How you can take the slope formula, apply a limit to it to get a derivative. And that's really where derivatives come from. And then some very nice person came along and found all those shortcuts for us, so we don't got to do this. Because like I said, it is a lot of writing. So the question is going to come up today, so I'm going to answer it up front. Why are we doing this? Because it's a lot of work, and we already know how to get the answer with a very short and easy method. The answer is because, well, there's two answers. One is because you asked in the beginning of the year, at least always somebody does, why does that work? Why does putting the coefficient in the front and then taking one off the power, why does that give you a derivative? I'm answering that question now. So that's one reason why I'm doing this. The other reason is because even though the type of questions we're going to be doing today are not exactly on the AP test, believe it or not, so I'll get to that in a minute. They're not exactly on the AP test. The process you go through, there's a short little quippy question that they ask a lot of the time that you wouldn't know how to answer unless you knew this process. So the question they actually put on the AP test is really short and easy, and we'll get to those. But that won't make sense until we do this. So there is a reason we're doing it. But pretty much this long, drawn-out process of finding derivatives we're going to be working on today. After this chapter, I might toss it in just to keep it fresh in your brain. But we won't drill it too hard after this chapter because, honestly, it's not really a big AP question. Okay? But it's pretty cool. Something you guys can understand. So it's definitely worth looking at. All right. So let's begin here. I want to start off where we began a while ago. So first of all, I'd like you guys to draw this picture, okay? You don't need the blue line on there, okay? So I'm going to get rid of that blue line really quick. But I'd like you guys to go ahead and draw this picture really quick. I'll pause for you. So you guys have this picture. Now I'm going to put that little blue line back. Bonus point time. What is the blue line called? It's called a secant line. That's right. All right. I have another question coming, so don't get too settled there. Let me write down Marco's point first. All right. The slope of the secant line tells you the. Let me try this guy here.
It tells you the tangent.
It's a good guess. I'm gonna go to Brody. It's called the average rate of change.
Did you ask what the slope was?
Let me see. Brody Freeman.
Mr. Bailey, I would have said that.
I know. I heard you getting. I just want to. I'm sorry. So let me ask you this, Nate, because then I'll come to you because you've been tracking with me pretty good. Now what we did was we took this point and I had you guys move that point a little bit closer to the starting point, and then I made you find the slope again, and then again, and then again, and then again. And every time we move that point closer, the slope of that little blue line is changing. Now, this graph won't do it because it's undefined when you make those become 1 point. But Nate, when those 2 points become 1 point, the secant line becomes a...
I don't know.
Let me go to work this time. It becomes a tangent line because it's only touching your curve at one point. So Nate, I'm going to come at you with one more shot. Ready? What do we call the slope of the tangent line?
An instantaneous.
Yes. Okay, good. So that's it. This is an important question, right? I mean, if you have a constantly changing speed, right, the best you could do in pre-calculus is find, well, what's the average speed? But then some guy comes along and thought, I want to find what's the speed instantaneously. And so that's it. And so basically the way I had you guys do it at the beginning of the year is I had you guys, delete some stuff here. I gave you guys a worksheet, and I had you find the slope of that blue line repeatedly, and I had you make a table of all the slopes, and pretty soon you saw, oh, that slope is getting closer and closer to a certain value. That's a limit, right? And what that was your instantaneous rate of change. Now, what do we call an instantaneous rate of change, though? It's a derivative. It's slope, but it's a derivative. So I just connected two major ideas in calculus there. I want you to miss it. It's a derivative, and it comes by taking a limit. Okay, so slopes are really, or derivatives are really. Now I'm gonna write something, but I don't want you guys to write it because I'm gonna make it look different in a minute. So I'm gonna call this point here. I'm gonna call this x1, y1, and I'm gonna call this x2, y2. And as you guys know, the slope of the blue line represents the average rate of change, right? So the slope between those 2 points, as you guys know, is y2 minus y1 over x2 minus x1, right? Okay, so that's the slope of your secant line, which is your average rate of change. But I want to find the limit of this thing as those 2 points become 1 point, all right? So to do that, though, I have to use some different symbols. So I'm not going to use y1 and x1 and x2 anymore. I'm going to change it up a little bit. So here we go. This is where I would like you guys to start writing. I'm going to call this point, I'm going to call that x value x, okay? The y value, though, I'm going to call that f of x. So let's label that point as x, f of x. And now I'm going to do something that probably will seem weird and stupid, but it serves a purpose, I promise. Okay. Now, don't write this. Just pay attention for now. Let's say that this x value was 4. And let's say I went over 9 spaces. So I'm just going to draw an arrow here. And I'm going to say that arrow is 9 spaces. What is this? 13. So you just basically do 4 plus 9, right? Okay. But we're not working with numbers. We're working with symbols here. So that distance between those 2 points, I'm going to call that, if this is x, I'm going to call that distance, and this is where I would like you guys to start writing again. I'm going to call that distance delta x. Yep, there you go. Delta x means the change in x. So that just means how far over to the right did I go. Now, if this is x and this is delta x, by the time I get underneath of this point, what's my x value? But you have kind of the right idea. X plus delta x. There it is. So it's x plus delta x. So we have our starting point plus the amount that we went over, correct? So that's my new x value. Now, if that's my new x value, what's my new y value going to be? There you go. It looks ugly and stupid, but it serves a purpose, I promise. Okay, so my first point is x plus delta x, f of x. My second point is x plus delta x, comma, f of x plus delta x. Okay, and all this is fancy writing for x1, y1, x2, y2. So what would my slope formula be here? It would be f of x plus delta x. Good. Minus f of x. There you go. So let's stop there for a second. Y2 minus Y1. You guys are writing this with me at this point, right? And then I don't want you guys to write the bottom. Okay? But I'm going to write the bottom. The reason I don't want you guys to write the bottom is going to make it look simpler in a minute. But what's x2? So there's x2 minus x1. Now the reason I didn't want you guys to write this is I'm going to simplify it. What can we do in the bottom here? Those cancel, right? And so what you're really just left with is what? Delta x. So that's what I want you guys to write. Is just go ahead and put delta x. So as ugly as this thing looks, okay, I want you to understand that's just y2 minus y1 over x2 minus x1 written in a really weird way. Okay? But why did they do that? Well, as I bring this dot closer and closer to my starting point, what happens to the delta x? It gets smaller and smaller and smaller. What would delta x be? What when I get to that point? It would be 0, right? So what we're doing is we're taking this slope formula, and I want to find what's the limit of this thing as delta x approaches 0. Right? What that will give me is the instantaneous rate of change, also known as a derivative. That's what derivatives really are. They are the limit of your slope formula. Just for vocabulary purposes, it's not a big deal, but I'll tell you, this piece right here is called the difference quotient. I don't think you really need to worry about that too much, but, you know, I don't know, it might come up. So there it is, you guys. That's what I want you guys to know really well today, is I want you to understand what this all means, okay? This looks crazy, but I want you to get it. This is really just y2 minus y1 over x2 minus x1. This is y2 because you take your starting x value and you add a little bit, right? And then you have your slope formula. Then I want to find the limit of this as that little difference becomes nothing, and therefore the 2 points become 1 point, and you end up with an instantaneous rate of change, which is our already very familiar friend, the derivative. This is what derivatives really are. This is what's called the limit definition of a derivative. Okay? So let's go ahead, and what we're going to do is I'm going to prove to you today. So here's our task for today. Our first example is going to be this. Yeah.
But wouldn't that always result in once the 2 points become 1? Wouldn't that always result in an undefined constant?
Great question. So Marcus asked, won't this always be undefined? Well, the answer is, do I have a discontinuity? Yes, because if I plug in 0, I get 0 on the bottom, and that's no good. Matter of fact, you get 0 over 0. Now you're just thinking, L'Hopital. You can't use L'Hopital, so we're not going to use L'Hopital. The thing is that is a discontinuity, but guess what kind it is? It's removable. Every time it's going to be able to be eliminated, and we'll do direct substitution. So here we go. So I'm going to start off with, don't write this, just watch. This is going to be our first function for the day. Now you guys already know what's the derivative? 2. But I'm going to show you how this gives you 2. And it's a lot of work. Why are we doing this? To answer the question, why does this work, first of all? And also because it'll help us answer a little AP question we'll get to later. But ultimately, we won't have to do that too often in the future. Okay? So, here we go. Let's do some math. So, example 1. Here's how the question will be asked. Use the limit definition of a derivative to find the derivative of this function. Okay. So we want to find the derivative of this. What's the instantaneous rate of change? Well, we need to find out what's our y2. Our y2 comes about by plugging in our x2. What's our x2? Our x2 is x plus a little bit more, which we call delta x, right? So I'm going to take my function, I'm going to plug in x plus a little bit more. This is my y2. So let's do that first. So I'm going to plug in x plus delta x into this function here. There's my function. And I'm plugging in for x plus a little bit more. And then I'm going to simplify that. Okay? So now that I know my y2, I'm ready to use my limit definition of a derivative. y2 minus y1 over x2 minus x1. But we're not going to use the algebra one. We're going to use our new calculus one, our new fancy formula. Here we go. Step 2. We're going to use this formula. The limit as delta x approaches 0 of f of x plus delta x minus f of x, y2 minus y1, over x2 minus x1, which simplifies to just delta x. So here we go. So it's always going to look like this. What's going to change is what you put in these parentheses. So this is our y2. What did we get for our y2? Yep. And then over here goes f of x. That means your y1, the original function before you plugged in a little bit more. So what goes here is just the original function. At this point, we're just going to find the limit, okay? The steps are going to be pretty similar, though, for a lot of problems, so I'll kind of write those out for you a little bit. But so let's say I wanted to find the limit of this function. What would you guys do first to find this limit? And that's not going to work, right?
Yeah.
So we can't do direct sub yet, but yeah, technically you are supposed to start with direct sub. But now what would we do? Good. We talked about factoring. None of those factor. Any other thoughts? That's an interesting thought. So it's a little bit different, but let's just think, let's simplify it. So if I just ask you guys to simplify this on the top, what would you do first? You're going to distribute the negative, right? So let's do that. So step 3, we're going to find our limit. And a lot of times, the first thing you're going to do is you're going to distribute. I mean, this is not always true for every problem. For the ones we're doing today, it probably will be, but in this case, we're going to start by distributing. But the real answer is just simplify. So if I distribute here, I get minus 2x plus 3. What else can we do to simplify the top? Yep. And, oh wait, did I do something wrong?
Yeah, I think it was minus 3.
Oh, this is supposed to be a minus 3, you guys. I goofed. Can you guys change that to a minus 3? Sorry. So the 3's also cancel. So that's the next step, is to combine your like terms. Let's see what we have left. You're right. Yeah, but I'm going to write that as a separate step because it's a different reason, but yes, you're right. So here's what I have left on the top, right? 2 delta x. And on the bottom, I've got delta x. Now what do we do? That's removing the discontinuity right there. So I'm going to call it remove the discontinuity. But really what it boils down to is just reducing. So what I'm left with now is the limit as delta x approaches 0 of 2. Now when you have a constant, what's the limit?
2.
It's just going to be the number. And didn't we say the derivative was going to be 2 anyway?
Oh,
So aren't you thankful for the shortcut? But there it is. There it is.
whoa.
So we just did the slope formula, and we found the limit as the distance between the 2 points went to 0, and we were left with 2, and that's your instantaneous rate of change. Okay? So the last step is just to find your limit. So this is how you really do derivatives, technically, even though nobody does it anymore because we have the shortcuts. This is how you really find derivatives. All right. So you guys ready for a practice problem? Here's one for you. Student practice 1. Okay? I want you guys to find the derivative of f of x is equal to negative 3x plus 5. Now we already know what the answer is. What is it? You should get negative 3. But I'm going to make you prove it now. So that is the limit definition of a derivative. I like to start off with linear functions just because they're simpler. Of course, you could do this with any function. When you start getting into things like trigs and ln's, you need a lot of like identities and things to get through it. I usually end up making those like extra credit questions. But polynomials, we're going to work with polynomials. So we're going to take it up a notch to quadratics. But before we do, I want to review something with you guys. I want to review with you how to multiply binomials quickly. I know you guys probably already know that this is like that, right? And you do the box method, and you got it, right? But there's a fast way to do binomials that are being squared. Here's how it works. And if you want to write this down, you can, because you'll probably need it if you don't already know it. But basically what you do is you square the first term. So my first term is x. So if I square that, I get x squared. Then you square your last term. So if I square that, I get 9. The middle's weird. The middle is first term multiplied by your last term times 2. So x times 3 times 2, which would be, it's a shortcut. So let me demonstrate another one for you. Ready? Let's say x minus 4 squared, right? If you square x, what do you get? Last term. Middle term will be x times negative 4 times 2. There it is. So it's much faster than foiling or doing the box method, so you want to be familiar with it. Okay? I'll throw in at you guys. Let's just practice one real quick. Try this one. X minus 9 squared. Okay, so what we're about ready to do is we're gonna need that shortcut in a minute here. So let's go ahead and jump into an example that involves some quadratics. Example 2. Let's say I said I want you to use the limit definition of a derivative to find this derivative. Okay? I'm not going to write the directions again, but that's what we want to do. We want to use the limit definition of a derivative to find the derivative of that function. Okay, so the first thing that we do, right, step 1, is we want to figure out what is f of x plus delta x, right? That means I'm going to go through to my function here, and I'm going to replace all the x's with x plus delta x. So first thing is that guy, and that's why we just talked about the shortcut, right? Save us some time. So this will be, the first term is going to be x squared Then we're going to have a middle thing in a minute. I'm going to do the last term though. What's the last term going to be? Delta x squared. And in the middle, what are we going to have? 2x times delta x. So here we're going to distribute. And we got that. So there's your y2. Yeah. Here we go. Step 2, we're ready for our limit definition of the derivative. You guys ready? So x2 minus x1 on the bottom. I'm going to need all that space probably. It's very long. All right. My y2, this whole thing, comes in the first set of parentheses. And then my original function goes over here. Now to save writing, I don't want to rewrite all this again, and you don't really have to either, but I think what we can do is we can just kind of show our work on one step here. So the next thing we do is distribute, right? And that's going to make this x become a negative x, this 3 become a positive 3, and this 1 become a negative 1, right? And then those three things are all going to cancel out with something on the other side, right? So the 1 cancels with the 1, the 3x cancels with the negative 3x, the x squared cancels with the x squared. So distribute and combine, right? And here's what I'm left with. Everything on the top should have a delta x at this point because we canceled everything else out. And that's what allows us to remove the discontinuity. So what we're going to do now is we're going to divide everything by delta x. I'm going to show my work like this for this one time, but I won't do it anymore. So I just want you guys to kind of see what's happening here. What I'm going to do is I'm going to divide each one of these by delta x. So I'm going to write it specifically this time like this. But in the future, I won't do this step, okay? I'm just doing it for the first time here so we can kind of see on our notes what's happening. So I'm dividing each term on the top by the bottom. And so here, those cancel. And I'm left with 2x. What would I be left with here? And then here? Those cancel, so it's 3, right? In the future, what I'm going to do is this. I'm just going to go, that cancels that one of those, and that one. That's how I'm going to show my work in the future, okay? All right. Now we want to find our limit, which we can find by doing what? Direct substitution. So if that becomes 0, what's the answer? 2x, which is our derivative, which we knew it was supposed to be in the beginning, right? Look at your original problem. X squared minus 3x. If you do your shortcut, 2x minus 3, right? And there it is. All right. So we're thankful for the shortcut, aren't we? Okay. I'll let you guys practice one like that. X squared minus 5x. So see if you guys can find the derivative of this function using the limit definition of a derivative. All right, guys. Let's chat our way through it here. So I'm just going to start off with this. And Zach, I'm going to ask you, what did you put here?
So first x squared
Uh-huh.
minus 5 over minus 5x. Wait,
No. I don't think so. No. Yeah. So what it should be is if we were to plug in our x plus delta x here, right? And then we FOIL this out, right? This will become 2x delta x plus delta x squared. This will become minus 5x minus 5 delta x. Now how about the second set over here?
what about this being right?
Yes, it would. Okay. And then after that, we're going to distribute, right? And so this becomes a minus, that becomes a plus, and the x squareds go away, and the 5x's go away. And so what we're left with is 2x delta x plus delta x squared minus 5 delta x all over delta x. And then after that, we cross off 1 delta x from everywhere to reduce it out, which leaves us with oops, got something there. Oh, I guess I need to write that now. So now we do the limit with direct substitution, and we end up with 2x minus 5, which we could have figured out very quickly in the beginning anyway, right? But, so on your homework, make sure you guys don't just write your answers, right? Because I want to see you guys deriving the answers through this process. I know you guys know how to do the shortcuts. That's not a problem. I want to see, can you do the limit definition? I'm going to demonstrate one more type of example, and then we're going to call it a day. The last one's not hard. It's actually really fast and easy, but it's just weird. So I want you guys to see it. Are you guys ready? One more? All right, suppose I gave you this. All right, so first of all, we already know what the derivative is here. What is f prime of x? It's just going to be 0, okay? So let's keep that in mind. But, so the first thing that we want to do is we want to find out what is f of x plus delta x, right? So what is f of x plus delta x? It's 5. It doesn't change. There's nowhere to plug this stuff into. So f of x plus delta x is still just 5. So therefore, whenever you do your limit definition of a derivative, what's your y2? y1? And we end up with this. 5 minus 5 is 0, right? Now in this case, what's weird here is that you can't cross a delta x off because there's not one on the top, right? So what do we do about that? Well, what we do is we use some basic math common sense. It's not obvious, but it's common sense. Here we go. 0 over anything is 0. Doesn't matter what that delta x is. It's 0. And therefore the limit of 0 as delta x approaches 0 is 0. So that was kind of a weird one. I just wanted to show it to you. But the other ones kind of follow, you'll see tonight, kind of follow that same principle that we've been looking at. So that's it, guys. We're all done.